All right. Hi, everyone. So we're very happy to continue with the special lectures by Mikhail Khovanov on universal construction, foams, and link homology. And today is going to be part B. Thank you, Mikhail.
Thank you so much, Hisham. So last time we discussed this interesting evaluation and where we had a form F in R3 subject to suitable conditions, and we assigned to it evaluation of F, which took values in the ring R, which is symmetric polynomials. So we can use, for instance, elementary symmetric functions and three generators, a subring of R prime, which is polynomials in x1, x2, x3. Characteristic of case 2. And from this, we can build state spaces. So maybe let me try to write bigger. Spaces, state space of a graph gamma, where graph gamma is planar Chavelin graph. And the sphere is functorial, so given a cobordism between these graphs, so given a form with boundary, it induces a map. So if you have a cobordism, this is a very special example of a cobordism. In this case, the bottom graph, gamma null, has no vertices, just loops. Top graph, gamma 1, has two vertices. Any cobordism was formed gives a map from the state space of gamma null to the state space of gamma 1. So if this is cobordism as F, so we can call it bracket of F, the map induced by F, and we get, so as we mentioned, we know that we get a TQFT for reducible graphs, those where we can always find a region of degree at most 4, and that can be reduced. And otherwise, it's only what we call a topological theory. Well, we don't know. We don't know for general graphs if it's a TQFT. There's additional grading. So this grading comes from thinking of xi's. Xi's, they come from dots. Remember, we have floating dots, and whenever we take a coloring, whenever we form a coloring of our form, this dot becomes one of the xi's, depending on the choice of the coloring I. So it contributes to the evaluation. Maybe let me recall that the evaluation was FC, was the product xi to the di of c, the number of dots on facets colored I divided by the product xi plus xj, to the chi, I'll just write chi ij of c divided by 2, which is chi ij of c, is the OA characteristic of the bicolored surface fij of c over 2. And F is the sum over colorings of C. So there's additional grading everywhere, where we set degree of xi to 2. And if you have, so that bracket gamma becomes a graded R module. So let me point out some simple examples. The simplest examples is when the graph is gamma is empty. The graph gamma is empty. The state space of gamma is just the ground ring. So when gamma is empty, what would our construction give? We should look at all cobordisms from into this empty graph, modular evaluation, modular universal construction. In this case, so this is your empty graph, so you're looking at forms below this empty graph, form F1. The universal construction means you say that two of the linear combinations of these forms is 0. If no matter what you add at the top and evaluate, you get 0. But this just depends on the bottom diagram. So you can just evaluate this thing below the empty graph. So this is just the ground ring R. if your graph is a circle in the plane, you can check that, for the circle, you can check that its state space is isomorphic to a rank-free module over the empty graph. So, and it turns out to be, so it's R of, let me put here, y, divided by the universal polynomial, y minus x1, y minus x2, y minus x3, which over this ring we should write as y cubed minus e1y squared plus e2y minus e3. And again, minus and plus are interchangeable because we are in characteristic 2. But you see that this can be identified with homology. I'll write it here. We can identify this with the homology here of the U2 equivariant for a point with coefficients in the field K. That's symmetric functions in 3 variables. U3, symmetric functions in 3 variables. And for the circle, we can, it's that algebra. Let me call this algebra A. And we can identify it with the equivariant homology, again, U3 equivariant homology of CP2 with coefficients in K, and it's that ring. And if you look at the next graph in complexity, the theta graph, we call it theta graph. Well, again, it has various structure. For instance, if you can add a little circle, and you can create a cobordism from a little circle union this graph to this graph. So you can create a cobordism like this. So it tells you that the state space of this graph is a module over A in many ways, in 3 different ways. So one possibility to get a module over homology of CP2 in 3 different ways is by taking the flag variety. Take variety of flags in C3. So there's a subspaces L1, L2 in C3 of dimension 1 and 2. Then you can look at, there's a forgetful map into CP2. You can forget L2. Or you can use the Hermitian structure to form the complement to L2. And you can also form the complement to L1 and L2. And that gives you 3 projections onto CP2, which are all P1 bundles over CP2. So you get 3 maps this way, which gives you 3 maps on cohomology going back from cohomology of CP2 into cohomology of full flag varieties, 3 possible ways. And so it turns out that this is the right answer. You can check that the state space of this graph is cohomology, equivariant homology for U3 of the full flag variety FL3 over K. But beyond this gets complicated. For graphs, maybe we can call this something. So B. So let me, in 5 minutes, I'll tell you one of the motivations for this construction. But another motivation came from a work of Kronheim and Mrovka. Where they study certain homology theory for 3 orbifolds. So 3 manifolds with orbifold structure of a very special kind. So they're orbifolds. They can have orbifold lines, line with the orbifold structure z bod 2. So you just take the plane, modular rotation by pi. So that's a z mod 2 structure. And these orbifolds can have vertices, where 3 of these lines come together. And the vertices correspond locally to the quotient of R3 by the Klein for group V4. So V4 is the Klein for group sitting inside SO3, the group of diagonal matrices. So if you look at the V4 action on R3 and mod out by that action, you'll have 3 singular lines with this orbifold structure. And now if you have a free manifold, you can take any trivalent graph and think of it as an orbifold. And of course, it almost never lives to an actual manifold. It's just normifold. And they developed homology theory for this orbifolds, a version of instant-on floor homology. And their theory, it's a single group, so let me call it Km, of a manifold or orbifold M3. It's a single group over F2, or a single vector space over F2. And so they show, they specialize to the case then you just have a graph gamma in R3 or S3, which is possibly knotted, trivalent graph, possibly knotted. In R3. And so they have a non-degeneracy result saying that their homology, I'll just write Km of a graph gamma, is zero. So it's zero if and only if gamma has a bridge. So there's a two sphere S2 that intersects the graph at a single point. And then the homology is zero, otherwise it's not zero, which requires using instant-on floor homology and the work of Gabai to prove this result. But then they specialize to planar graph gamma, and so they have a sort of, the initial conjecture is that the rank over F2 of their homology, gamma is exactly the number of tight colorings of gamma. The number of colorings of edges into three colors, such that every vertex in the colors is distinct. So if this conjecture is true, then this would imply the four-color theorem because of their non-vanishing result. But that's not known. But there is definitely a relation to the combinatorial structure we discussed last time. And the relation is that if you so we had the state space of gamma coming from the variation of a form with values in R. So R has the surjective map onto K, where you send E1, E2, E3 to 0. You send E1, E2, E3 to 0. There's this homomorphism into K. So let me call this composite evaluation. The homomorphism is really from R. So it's homomorphism from R to K, the ground field. Just kill everything in positive degree. So let me call the composite evaluation F0. So it's just an evaluation in K. So now you can repeat the universal construction in this case, and you get a state space gamma 0, which is just a K module, a K vector space. Yes. You can check whether it's fine dimensional. It still has grading. Where degree of a dot is 2 in particular. So if you put together work of Khovanov and Brovka and what we did, then you'll see that that the state space gamma 0, it's a subquotient of Khovanov and Brovka of gamma. So now both this and Khovanov and Brovka are vector spaces over F2. And you have the inequality on ranks, rank over F2 of a version of our story of the state space is less than or equal to the number of tight colorings, gamma, and less than or equal to the rank of Khovanov-Brovka homology of gamma. And this is known to be non-zero for bridgeless graphs. So, and kind of again, a conjecture, possible conjecture that these ranks are equal, which would imply, the four-color theorem. It would give a sort of conceptual explanation for the four-color theorem, but that's open. so that's, and so some computations. So this is, of course, this is equality for reducible graphs. And again, so for reducible graphs, so we get some deformation, some quantum version of a number of tight colorings, because you can look at graded rank of F, or graded rank of F null, and we get a polynomial that at q equal to 1 specializes to number of tight colorings of gamma. But this is not the familiar deformation of a number of tight colorings comes from studying representations of UQSL2 and using the three-dimensional representation V2, three-dimensional representation. This is the so-called Yamada polynomial. And it quantum deforms the number of tight colorings. But you can check that this is a different deformation. Deformation using the graded rank of the state space is a different deformation from the Yamada polynomial. But we don't know how to compute it in the non-reducible case. But already in the reducible case, it's different. So that's another relation is to quantum SL3. Maybe let me pause for questions. Okay, so let me explain the relation to quantum SL3, which is much older than the rest of the story. So the relation is that if things are now orientable, and more specifically, if the graph gamma is bipartite, if graph gamma is bipartite, so that means that vertices are split into two types, and there are orientations on edges. We can orient the edges such that every vertex is either an in vertex or an out vertex. In or out. So that then every edge goes from an out vertex to an in vertex. So these graphs are, with such planar graphs, they're all reducible because you always have either a region of valency 4, which can be reduced to the union of these graphs, or you have a region of valency 2, which can be reduced to this graph where you have a circle, which is also reducible to nothing, just erase the circle. So in this case, there are no difficulties due to the possible regions of valency 5 and higher, as in the case of the dodecahedron. So it's always reducible, so you can compute your evaluation. And in this case,
I'm sorry.
Yeah.
Couldn't you have like hexagonal regions?
Yes, but because of the OA characteristic argument, there's always a region of size 4, size 2, or size 0.
Okay, thank you.
Yes, and in fact, the story of planar graphs that are bipartite, trivalent graphs that are bipartite, this goes back to Kuperberg, who constructed he wrote quantum SL3 invariant using these trivalent graphs by thinking of this vertex as a space, as a generator of the invariant space. Invariant space of quantum SL3 in the third tensor power of the fundamental three-dimensional representation of quantum SL3. So V is C3, V is C3, or I think of Q as a generic complex number. And this picture corresponds to the invariant in the third power, invariant vector in the third power of Q. And then his relations for planar graphs are the value of circle is quantum free, so it's Q squared plus 1 plus Q minus 2. If you have a Deigen region, This can be simplified to quantum 2 times vertical line. And if you have a square, that reduces to the sum of these two diagrams. And that's enough to compute any planar trivial graph. And for any planar trivial, let me call this invariant polynomial P of gamma. It lives in Z plus QQ inverse. It's the Kuperberg invariant of the planar graph. And you can think of it as another clarification of you can think of it as a quantization of a number of tight colorings of such graphs, because you see quantum 3, quantum 2 instead of the usual 3 and 2. So this is a sort of quantization of a number of tight colorings of planar bipartite graph. And this can be used to define quantum SL3 invariant of links using linear combinations. You say that the quantum SL3 invariant of a crossing is a linear combination, Q minus 2 invariant of this simplification minus Q minus 3 invariant of this simplification. So crossing with this say positive orientation, it's this combination, and for negative, it's a similar combination, but without minus signs in the exponents. But of course, for links L, P of L is no longer positive. Z plus, so it's in just integrals, Z QQ inverse. So the original motivation for forms, and that was many years ago, around 2004, was to try to clarify the Kuperberg invariant of links, lift it to a homology theory for links. And the step was to first categorify the invariant for planar graphs, because it has positivity property. So that should be easy to categorify. You can expect it just to lift to a graded vector space. You can use a version of this form construction. You can say we want to categorify this P of gamma. So we want to upgrade P of gamma to homology theory for gamma, such that this is the graded rank. And then if you want to have this homology for planar graphs, if you have a cobordism between these graphs, that should add interaction, that should add a homomorphism. So you want a topological theory or a TQFT for this cobordisms between graphs, and they would be called forms. And then you can just guess when the way we constructed this homology was to, again, it was using universal construction. So look. So now graphs are oriented, such that at every vertex it's in or out. Now you look at forms that are also oriented. So at every edge, the orientations are at each of the three facets. At this edge, they are they can, as you go from one face to the next, they're reversed. So you reverse orientation. But now these forms have very simple properties. So we call them oriented SL3 forms, as opposed to the unoriented ones here, because we didn't have orientations on graphs and on facets. Oriented SL3 forms. And those, they're much easier to evaluate, because such a form F, it has no vertices. So there are no singularities of this form. So there are just singular lines, and for closed forms, they become singular circles. So what you can have for a closed form, you just have a bunch. You can have a bunch of singular circles that are disjoint, and these are also facets. These are facets. Then such form doesn't need a fancy variation that we saw yesterday. We just take such a form and we say a circle should correspond to homology homology of CP2 over U3. And we know how this works. So we have, this is a Frobenius algebra over homology of the point. So we can write down a Frobenius algebra decomposition as a sum of basis elements here and dual basis elements here. So this allows us to do all reductions, and we can do the surgery nearer at every seam, at every circle, at every seam. Then we do these reductions at every seam. So at seam, at the circle, we have 3, half, 3 annuli coming in. And we do this reduction at each annulus. Reduction. As a result, you get surfaces that are easy to evaluate using a TQFT. And you also get theta forms where you have 3 facets and some number of dots on those facets. And those can be evaluated by thinking of them using homology of full flag variety FL3 for U3. So they, let me. So you think of this element as the unit element in homology in this ring. Let me call this B as 1 in B. And putting dots will give you monomials, the usual monomials in the homology ring of equivalent homology ring of full flag variety. And then capping it off is just the trace homology ring in the there's a trace in both equivariant and non-equivariant case, and that's your evaluation, the evaluation of, you close up and trace tells you how to evaluate. And this works, so this is in some sense much more elementary than our fancy evaluation that required colorings. And this works for SL3, and this leads to a lifting of, so again now for these oriented forms, there are no vertices. We can evaluate using the rules for homology of CP2 and homology of flag variety.
Mikhail,
yeah.
Can I ask a quick question?
Yeah.
So it seems like you're doing the something that's equivariant here, right?
Yes. So we're doing equivariant.
So
there are 2 versions. You can do non-equivariant, in which case the state spaces are just vector spaces.
So if you want to categorify the SL3, you would do the non-equivariant one, right?
Either one works. So let me just make some more space.
How would you get something finite dimensional, though? I mean, because
Yeah. So if you do non-equivariant versus equivariant, then here the homology of the empty graph or empty link is just Z, and here it's Z in E1, E2, E3. The equivariant homology of a point. And for the circle, here you get non-equivariant homology of CP2, and here you get equivariant homology. And for the trivalent graph, for this graph, you get usual homology of flag variety FL3, and here you get equivariant homology.
but in the third column, can you calculate this graded Euler characteristic? Or
You just take grade, so you have a free. So in this case, everything is reducible. So state space of a graph is a free module, free graded module over the state space of the empty graph over this ground ring.
Okay.
So you can take graded rank, and you can take graded rank here as well over Z.
Understood. Thank
Yes. So the integral case, I did this around 2004, and this case was done by Pedro Vaz and Marco McKay a couple of years later. But that was kind of much easier for us because we didn't have to deal with vertices. So dealing with vertices, so far the only combinatorial approach is to use this form variation and using that formula that really came from Robert and Wagner's work in the GLN case. So in the SL3 case, an oriented situation is much easier because you don't see these vertices And you can just build everything out of this data, the homology of CP2 and flag variety. And so unoriented case was done much later, much more recently. But when it relates for complicated graphs, on one hand, we don't know fully the state space, but it also relates to Kontheim-Ambrovka gauge theory and the four-color theorem. And also, it's one step to get to homology of links. So now we want to categorify Kuiper-Berg invariant of links given by these rules. So Kuiper-Berg invariant also satisfies the scaling relation. The scaling relation is that q squared times polynomial of a link with this crossing minus q minus 2 polynomial, q cube, polynomial of the q cube minus q minus cube is equal to q minus q inverse polynomial of this link. So you can check what this relation follows from these relations. And if you replace q3 by n, you get the SLN quantum invariant of Reshetikhin and Turaev. And so none of these difficulties related to forms and graphs appears when this is 2, when the codification is the kind of is the link homology, and you kind of convert a crossing into a complex corresponding to the two resolutions. So there are no difficulties, there are no issues related to creating state spaces of graphs and working with forms. So it was much easier, the SL2 case. But for SL3 case, we had to use this universal construction for oriented SL3 forms, getting state spaces for oriented planar trivalent graphs. And to do the last step, to get to homology of the link from homology of planar graphs, you want to convert this, you want to lift this relation to a long exact sequence of homology groups. So you want to assign a chain complex to this diagram, which is going to be the cone of the map of chain complexes for these two diagrams. And indeed, there is a canonical map. There is a canonical map between the state spaces for these two graphs given by the cobordism, given by the form where you go from two parallel lines to this graph using a cobordism which can be called a singular saddle. It's a little bit like creating a saddle, but in a singular sense. And so this form F induces a map. This is graph gamma null. This is graph gamma 1. It induces a map from homology of gamma null to homology of gamma 1. And you just take the corresponding cone of the map of these forms, and you can have stuff outside of this crossing that are also crossings. So you build up inductively for many crossings. You build up your complex as a iterated cone of the map of complexes for simpler diagrams with fewer crossings. And then you take homology of the resulting iterated cone, and you get homology of links, H of L, which categorifies P of L. If you take the Euler characteristic, this is bigraded. If you take the Euler characteristics, you get the Kuiper-Berg invariant P of L, which is the quantum SL3 invariant of links. And then, so after this, after this came out for SL3, so conversion, maybe I'll pause for questions. So how much time do I have?
We still have 25 minutes. Any questions?
So again, we're kind of the older story is for oriented graphs and oriented forms, and it leads to link homology. But you avoid the complexity of having forms with vertices. And so when you have vertices, you cannot localize along singular seams. You just have to come up with a formula for this form, which is kind of very, very complicated. And this had to wait many years. And it was motivated by Robert Wagner's work for similar forms for GLN in the oriented case. So when you do oriented case for SL3, there are no vertices, but for SL4 and high, you get vertices. So this, people also didn't have an approach, combinatorial approach to this homology for SL4 and higher until recently. So let me maybe say what happens for 4 and higher. So if you try to do this approach using variations, you run into forms with singular vertices. So for many years, people just used different, more categorical approaches to build these homology groups. So they would So on the categorical side, in the decategorified case, in the original quantum case, so you have a tangle. So it goes from some number of points on the bottom half plane, tangle T, to some number of points on the top half plane. So you color your components by representations of a quantum group. And the invariant of a tangle is a map from the tensor product. I'll call this maybe V underline, V lambda underlined, where lambda is a sequence of weights, lambda 1, lambda n, sequence of weights, to V mu underlined, where mu is a sequence of weights. And the invariant of a tangle is a map of representations of the quantum group corresponding to the tensor products V lambda 1, tensor V lambda n into V mu 1, tensor V mu m. And that's a representation from the category of tangles with colored by representations of the quantum group to representations of the representation category of quantum groups. And this is the original Shishkin-Turaev invariant of links. So codification requires lifting, realizing this tensor product as the Grothendieck group of some triangulated category C lambda underlined, and lifting this tensor product to a triangulated category C mu underlined. And then invariant of T is an exact functor. Let me write it as F, capital F of T, exact functor. And this category is triangulated. And then so to a functor, to a tangle you assign a functor. Composition of tangles corresponds to composition of functors. If you compute this functor on the Grothendieck group, you can identify Grothendieck group of C lambda with V lambda, with a lattice in the lambda. So if you pass the Grothendieck group, oh yeah, I'll use another one. So, yes, if you take the Grothendieck group K null, the category turns into an integral lattice V Z lambda underlined. In the sense it's a module over free module over ZQQ inverse, such if you tensor it with C, you get this vector space. And K null takes this category to a group V mu Z. And this functor, if you compute it on the Grothendieck group, gives you the Shishkin-Turaev invariant of a tangle, this map. But this is always a very complicated story. So in the sense that people usually would do it usually for the group G, for G being GLN or SLN, and usually for some representation. So minuscule representations are easiest, are the best. In fact, minuscule representations of GLN. But then people would, but it always takes a lot of work. So people would do this construction, for instance, for when categories C in one example, categories C lambda are highest weight categories, like category O, highest weight categories of representations of SLN. where this n is different from this n. So this is different from this n. And you need to take parabolic singular blocks. Singular blocks of the category of a high state category of SON. And the size of these blocks depends on the weights you have here and on the n. And this is restricted to exterior powers of the fundamental representation. So the weights are fundamental weights. And this is, but it's a very sophisticated piece of work. So it's kind of, so there are many people. So George Sasson. So prior to him, we did the SL2 case with Joseph Bernstein and Igor Frankl. I should also mention work of Kafarina Stropel, Vladimir Mazurchik, and others. So it takes a lot of work to put this together, to check that all these functors exist and have the right properties. So you realize these functors, they come from projective functors, Bernstein-Zuckerman functors, and cones of maps between them corresponding to bijoint. So it's a fair amount of work. And then people also found these categories inside derived categories of sheaves and suitable quiver varieties. That's work of Kamnitzer and Kautis, and later work of Rina Anna and Vinod Nandakumar. There's also work of Paul Seidel, Ivan Smith, Mohammed Abu Zaid, realizing these categories inside Fukaya-Floer categories of suitable quiver varieties again. But so it's always a huge amount of work to set this up. So, but for many realizations, in some cases it's known that you get exactly the same categories. In some cases you get break group actions, you get tangles, etc. But you don't. I mean, it's not. You don't know for sure that it's the same ones, but it should not be much different. And I should also say that for a tangle in the story, you get a functor ft. So for a tangle cobordism, you get a natural transformation of functors. So you have a 4D story. Before, on the Richtlichen-Toraev level, you have a 3D story. But now you have functors for exact functors for tangles and for tangle cobordisms, so surfaces in 4D subject to suitable boundary conditions, you have natural transformations of functors. And you can see relations to lots of interesting mathematics, lots of interesting category theory. So you locate the same categories and the same collections of functors and their interrelations through the story, through tangles and tangle cobordisms. But also so for SL2, for SL3, we had explicit combinatorial constructions of these categories and functors. And more recently, there was such a construction due to Lodry and Robert and Wagner. So I'll just briefly say how it's different from the evaluation I described yesterday. So in their construction, on the decagrified level, you use so-called Murakami, Atsuki, Yamada graphs. So you would decompose your crossing into a linear combination. In the simplest case, it's a linear combination of planar graphs where this sort of carries a weight. You put weight 2, put weight 1, put weight 1. And then you need to allow all weights. So you need to allow weights. Your lines carry weights, A, B, such that you can have a trivalent vertex where they merge into a line of weight or thickness A plus B. And vice versa, you can split a line of thickness A plus B into lines of thicknesses A and B. And you can build a planar graph out of this diagrams where thickness A changes from 1 to n. And for instance, in this evaluation, so for instance, the value of a circle of thickness A is going to be quantum n choose A. Quantum n choose A. So you expect that the whole theory can be categorified. So for instance, this circle, you would want the circle to categorify to the homology of the Grassmannian of A planes in Cn. Of planes in Cn. For instance, so you could see that already for the unknot, the homology must be very sophisticated, very complicated. And this is replaced by more complicated rules when the thicknesses are A and B. When there are more complicated rules with more complicated graphs. So then how is it done? It's done, well, you want to go one dimension up. So now you want to look at forms. And the forms will have facets of thickness from 1 to n. And in particular, forms can have a seam. This is a seam, where a facet of thickness A and facet of thickness B merge into facet of thickness A plus B. And you also have orientations. Orientations on edges, they lift orientations on facets. So on facets, you have orientations. So that along the seam, when you go from a thin facet to a kind of thick facet, the orientations are the same. But from a thin to a thin, they reverse. So then there is the Robert-Wagner variation of these forms. And you also, when you have a facet of thickness A, you can put a dot on it, but the dot is understood in a more general sense. A dot is an element, I don't know, G of the symmetric functions in A variables. So symmetric functions in, I'll put here, A variables A. So it's Z, Y1, Y sub A, S A invariants. So, okay. And this form, the form can have a vertex where, if you look at cross sections at the vertex, you see this transformation, which looks like associativity relation, something lines of thickness ABC. They sort of flip to the other side. So you have facets of thickness ABC, A plus B, B plus C, and A plus B plus C. And everything is oriented in a compatible way. So your form is built out of the seams and out of these vertices. There are four seams come together. So how to do the evaluation? And again, this is Robert and Wagner's work from 2017. To do the evaluation, So first introduce the notion of a coloring. Coloring. Now your set of colors is 1 through n. So that's 1, 2, up to n. So in the coloring C is an assignment to every facet. So to a facet of thickness A, you assign a subset, let me call it I sub 1, a subset of the set of colors of cardinality A. So now it's not a single color, but several colors given by the cardinality of the facet. To a facet of thickness B, you assign coloring I2. I2 is a subset of IN of cardinality B. And you require the kind of flow rule that to this facet of cardinality A plus B, you must assign the disjoint union, I1 union I2. In particular, they must be disjoint. It's empty, so the colors must be disjoint. And everything works, so this, at the vertex, you'll assign disjoint subsets I1, I2, I3 of these cardinalities. And then there are unions to the bigger facets at the vertex. And so this is the coloring. And now in the evaluation of Robert and Wagner, the evaluation of F with a coloring C is going to be, there is a certain minus sign, -1, so certain, to a certain 0, 1 function for F and C. here, so in the denominator, you put the following thing. You put the product over I less than j from 1 to n of xi minus xj to the exponent, the Euler characteristic of Fij of c over 2. So Fij of c, so these are bicolored surfaces. So this is Fij of c. It's the following. I'll write it as Fi of c, symmetric difference Fj of c, where Fi of c is a union of facets such that coloring contains I. So each of these sets can, for a given element I from 1 to n, it either contains I or it doesn't contain I. So if this one, for instance, contains I, then the union contains I. But this one doesn't contain I. So if you take all facets that contain I in the coloring, you get a surface. So you can check this property at the vertex as well. So you get a surface. And then you define Fij of c as symmetric difference. So you take facets that contain one of these, but not both. Symmetric difference.
Can I ask a quick question?
Yeah.
Mikhail, on the right-hand side board, if I understand the intuition correctly, A should be interpreted as the 8th exterior power of the fundamental representation?
Yeah, so here in this calculus, precodification, this is, it gives you Stichen-Derive invariant for SLN and exterior powers lambda A of V, but quantized.
How would I then see a coloring in this representation theoretic sense?
Well, you see it's kind of one-dimensional shadow because now your basis element here will be given by the wedge product of A elements from the basis of V.
So a coloring is a basis representation for...
It's related to the basis representation, but I think if you want a better fit, there's kind of more refined explanation for how to see shadow of this variation in this language. And there's a work of Robert from, I think, 2015, where he explains a kind of better evaluation for this graph that fits the surface story more.
I see.
But naively speaking, here you're coloring this, when you compute the state sum, you color this by a basis element here, and the basis element here will have the form Vi1, wedge Vi2, wedge Vi sub A, for some sequence I1, I2, IA.
And you symmetrize it in the formula.
I can sort of Q onto symmetrization.
I see. Okay, thank you.
So this is similar to what we already saw. And here you put the analogs of kind of dots to some powers. But here you have to put a product over all facets F. So in the facet F, you might have some function G in symmetric function of A. So you write G, but you replace Y, variable Yj, by the variable X, Cj. So you have your coloring for your facet. You have your color I1. It corresponds to X C1 has variables X C1, X C sub A. So you replace variables Y by variables X sub J, depending on the choice of your color. And there is this additional sign which takes into account all the characteristics of Fi's and some additional sign data. And this is the formula, and then the evaluation of F is the sum of Fc over C. And this is the original Robert Wagner formula. And there's lots of work to check that everything kind of matches, that you have the state spaces, they're finite dimensional, they are free modules, so the ground ring of symmetric functions in the axis. So the ground ring is Z, x1, xn, Sn invariant part. This is the ground ring. And there are no difficulties that appeared in the first talk related to the not being able to reduce. Here we can always reduce, but modular some additional terms. So you can check that this way. If you take the evaluation of forms using this complicated formula, you get state spaces that are free modules over R. They have grading, and the graded rank of the state space for graph gamma of this form is the quantum invariant. I'll just say P sub n of gamma, where P sub n is the quantum SLN. Probably better to say GLN, quantum Reshetikhin-Tarayev, GLN invariant of gamma. And we were able to do, well, they were able to do the story. This is specific to GLN and exterior powers of the fundamental representation, because intermediate step is to have this planar graphs. A simple example of such graph, such that the quantum invariant on these graphs, P sub n of gamma, is in Z plus Q inverse. So this positivity is essential. This positivity allows us to build homology groups in a relatively simple way without using complexes, just using universal construction and state spaces. And then after this, you define homology of links using complexes of the state spaces. And this is kind of the best case scenario. So we don't have anything like this for, well, if you take quantum SL2 and you take arbitrary representations, we don't have this kind of integrality and positivity available in, for instance, in the Q-spin networks. They're not integral, they're not positive. So this is one problem with doing something as canonical as the story for general quantum group and general representations. But for general quantum group, G and arbitrary representations, there's work of Ben Webster, where he refines tensor products of arbitrary representations of the quantum group and functors between them corresponding to tangles. So he does get link homology theory, but it's not known, so they're not functorial. And many other theories defined for similar situations, but not without this intermediate step where you have integral and positive integral structure, which allows for easy verification. In many other approaches, we don't have functoriality. In some cases, we cannot have them for obvious reasons. In some cases, it's unknown. But so, for instance, in this story that Nito told us about, you have this beautiful lifting of link homology to spectra, which carries much more information. But one kind of missing piece is functoriality under cobordisms, because your construction requires a braid closure of a link. And there are other examples of link homology theories that don't, I mean, they're not at the level of spectra, they're just homology groups, but which require presenting a link as the closure of the braid. And for them, we don't have functoriality either. So it's a big open problem to extend a number of link homology theories to make them functorial. But in this scenario, functoriality works out perfectly. And this is Robert Vaughan, and later follow-up work by Daniel Tibinauer, Michael Ehrig, and Paul Wedgick. So this is sort of for now, it's sort of the golden standard, the best case scenario. There is a purely combinatorial algebraic approach, but it's very sophisticated, requires this evaluation formulas. And there are a number of approaches using category theory, derived categories of coherent sheaves, category O, Fukaya-Floyd categories, and other examples. And I think definitely there are many interesting equations, such as understand the significance, find analogous formulas, maybe in statistical mechanics in 3 dimensions, for example. So I think there are lots of interesting open questions. So I think I'm probably out of time. Thank you.
Thank you. Further questions for Mikhail? Yeah.
The formulas for the evaluation of these foams
Yes.
are only for the exterior power.
They are.
Or also for other representations.
So form could be very complicated because this form has seams. It has these singular vertices, and you might have a very complicated connected graph with these vertices and seams. So for example, I yesterday I gave an example of an SL3 form where we start with a torus, right? And we add some number, just draw parallel disks inside meridional disk inside the torus, and also add. Let me change the color and add. Also add longitudinal disk, just several parallel disks. And you get a complicated form with many vertices and many edges, so a graph between them. And generally, if you just have beer, if you look at the form in the beer, I mean, it has generic singularities. So you'll see a form with boundary of this form. And I mean, so here is, I mean, I'm sure it's easy to come up with weights to make this a GLN form. But the variations are very complicated, and I want to point out that if you look at one of the simplest forms, basically you take a disk of thickness n, and you split it inductively into n disks of thickness 1, and you put m1 dots, m2 dots, mn dots, and you evaluate this form, and you get the Schur function S lambda. So from the evaluation, you see what is the Schur function S lambda for the partition lambda, which is m1 minus n, I guess, minus 1, m2 minus n minus 2, etc., m sub n for this partition. So in this kind of one of the simplest cases, you see Schur functions, but this has not been explored much. So for instance, what functions you get from other forms? You know that they're symmetric functions, so they're linear combinations of Schur functions, but there could be some more to the story beyond this observation.
Thank you.
Any other questions? Actually, I have a general question. So far the algebras have been of A type.
Yeah,
Can one consider other types, or is it interesting or not?
Yeah, so it's interesting, but it's highly non-trivial. So in particular, so a student at Columbia has been working on this, so she has partial results for B2. And so people have thought about BN types and DN types, but this question is subtle even for webs, because people spend doing webs in the BN, DN, CN types is non-trivial. They're not, the evaluations are not integral. Usually they're denominators. And so people are still working on webs. Even webs are subtle, but it's, I mean, it's sort of an open question to do this link homology theory for BN types and CN types. So we had some approach with Lev Rozansky and Anton Zaitlin using residues and Kapustin-Lee formula. So Kapustin-Lee has a certain residue formula to study evaluations of surfaces with some correlators in Landau-Ginzburg models. You can extend this formula to forms, and then at some point we worked on getting this formula from the residue, but it's still a work in progress, unfortunately. But we expect to get this from Landau-Ginzburg for forms, not for surfaces, but for forms.
Mm-hmm. Appreciate that. Thank you.
So just following up on Hisham's question, if you're not working in the AN type, then you don't even have a well-defined set of generators of the representation ring, right? So what would you even mean by labels for colors?
Well, you can. So I guess you can maybe have signed version of this. You have a subset.
But you have to.
I with a sign plus or minus for every element. Because in the BN case, you just see signs.
But you have to make some choice of generators, right? Like here, you took the exterior powers for the for the generators of the representation ring.
But you just take exterior powers and you don't worry about the spin representation. You just ignore the more complicated. I mean, if it's there, you ignore the spin representation.
I see.
You can just take exterior powers.
Mm-hmm.
Questions? If not, let's thank Mikhail again for
Thank
the
you.
very nice second lecture.